Hello, this is Richard Hammack's Calculus 1 course. We are in part 2 of the course on limits. Today, lecture 8, computing limits. Previously, in lecture 7, we looked at the problem of finding the slope of a tangent line to the graph of a function, which we remarked was a central problem in calculus. And in finding that slope, we realized we had to use a new idea called a limit. And our plan was, and still is, to investigate limits in part 2 of the course, and then return to slopes of tangent lines in part 3. So put tangent line slopes on hold for now, and look exclusively at limits, what they are, what they mean, how to compute them. At the end of lecture 7, we stated this informal definition. Suppose f is a function and c is a number. Then the limit as x approaches c of f of x is the number that f of x approaches as x approaches c. So this expression, which we read as the limit as x approaches c of f of x, stands for the number that f of x is getting closer and closer to as x gets closer and closer to c. We can draw a picture of that as follows. Here's the graph of f of x, and here is a number c. Now it so happens that for this particular function, f of c is not defined. There's a hole in the graph, which is actually pretty typical in limits. But that hole occurs at a y-coordinate of L. And in this picture, you can see that as x approaches c, f of x approaches the number L, which means, according to our definition, the limit as x approaches c of f of x equals L. So to see that, take a value of x and look at f of x, and now let x approach c and look at what happens to f of x as x approaches c. So x is approaching c, and f of x is getting closer and closer to L. As x approaches the number c, f of x is approaching the number L. If x were to the other side of c, and we look at f of x, it's above L, but as x gets closer and closer to c, f of x is getting closer and closer to L. As x approaches c, f of x approaches L. So L is the number that f of x approaches as x approaches c, which means that L is equal to the limit as x approaches c of f of x. Limit as x approaches c of f of x equals L. I'll draw a slightly different picture of this, and we'll look at it from a slightly different perspective. Here's the same f of x, the same c, and the same L. One way of thinking about the limit as x approaches c of f of x is to just look at what's happening for values of x that are really close to c, in some small open interval containing c, and ignore everything else on the graph. Just look at this strip that you get from the x values in this small open interval, and you have this small portion of the graph right here, and you can see that for these x values in that strip, your f of x values are pretty close to L. Your f of x values are very close to L. And I'll put the rest of the graph back there. But the idea here is that you could make this strip containing c smaller and smaller, and those x values inside that strip would correspond to f of x values that get squeezed into L. As this interval gets smaller and smaller and smaller, the corresponding x values in it have y values, f of x, that are getting squeezed into L. So with this picture, we can have a slightly more precise definition of the limit as x approaches c of f of x equals L. It means that you can force f of x to be arbitrarily close to L by restricting x to a small enough open interval around c. So by taking values of x in a small open interval around c, you're forcing f of x to be very close to L. And you can get f of x as close to L as you want. You can guarantee that f of x will be as close to L as you want by choosing this open interval around c with your allowable x values to be small enough. So for any open interval around c, take an x in that open interval, f of x will be up here. And if you want to guarantee that f of x is going to be closer to L, just make this strip here, this open interval, smaller. This is a more precise way of looking at the limit and defining a limit, because it could be that your function f of x looks something like this. It has some rather wild behavior. In this case, notice that as x gets closer and closer to c, f of x is below L, then it goes above L, then below L, above L, below L, above L. It's oscillating back and forth above and below L. So it's not strictly getting closer and closer to L. Sometimes it's going away from L or moving towards L, going away, and so on. But in the long run, as x gets closer and closer to c, your f of x values are zeroing in to L. So the takeaway here really is, as we stated up here, the takeaway is that the limit as x approaches c of f of x is the number L that f of x approaches as x approaches c, with the understanding that f of x could be approaching L, maybe as indicated here in this picture. Not getting steadily closer and closer to L, but going back and forth, but zeroing in on L. As an example, consider f of x equals ln of x squared over x minus 1. Notice that if you tried to plug in 1 to f of 1 would be ln of 1 squared divided by 1 minus 1. And ln of 1 is 0, and 1 minus 1 is 0, so you'd get 0 over 0, which is undefined. Well, that's fine. It just simply means that 1 is not in the domain of this f. But imagine you asked yourself the question, what about the limit as x approaches 1 of ln x squared over x minus 1? Let's see if we can find out what this limit is. So here x is approaching a number that's not in the domain of the function. What do you get? What is the function getting closer and closer to? Well, here's a graph of f of x equals ln of x squared divided by x minus 1 that was drawn with the graphing utility. And it has a nice smooth shape, looks like a nice smooth curve. It has a hole in the graph at x equals 1. Remember that f of 1 wasn't defined, so there's going to be no part of the graph over x equals 1. But otherwise, the graph looks like this. And it so happens that if you graph this really carefully, as I've done here, and you look at it, that hole appears to be at y equals 2. That's its y coordinate. And in this picture, notice that as x gets closer and closer to 1, f of x is going to get closer and closer to this number 2. As x gets closer and closer to 1, f of x gets closer and closer to 2. As x approaches 1, f of x approaches 2. From the other side, as x approaches 1, for this x, f of x is down here, but as x approaches 1, this f of x is going to move up closer and closer to 2. Let's take a look at that. So as x approaches 1, f of x approaches 2. So from this evidence, we would surmise that the limit as x approaches 1 of ln of x squared divided by x minus 2 equals 2. Now, we haven't really proved that because is this number really 2? Is the y-coordinate of this whole really 2? Would it instead be 1.999 or something like that? But just from this evidence, it appears that the limit is equal to 2. You could reinforce this if you wanted to with a table tallying x values that progressively get closer and closer to 1, like x equals 0.5, then 0.9, then 0.99, and 0.999, and so on. So 0.5 is here, 0.9 is there, 0.999. It's getting these x values are getting closer and closer to 1. And with a calculator, I've tallied the corresponding ln of x squared divided by x minus 1 numbers. And they start out at 2.77, a little bit bigger than 2. And as x gets closer and closer to 1, these y values, you can see they appear to be getting closer and closer to 2. So that's numeric evidence for the fact that as x approaches 1, f of x approaches 2. That the limit as x approaches 1 of f of x equals 2. The situation illustrated in this example is pretty typical for limits. We have a function f of x and a number 1 that could not be plugged into the function. 1 is kind of a bad point for this function. You try to take f of 1, it's not defined. Yet you can ask what is the limit as x approaches 1 of that function. And here we found that even though we can't plug in 1 to the function, we can take the limit as x approaches 1 of the function and get 2. So limits tell us about what happens to a function near a bad point. They give us information about how the function behaves around these bad points, like 1. And that's going to be very useful for us in calculus. Here's another example. You might recognize this from the previous lecture, lecture 7. Find the limit as x approaches 1 of x squared minus 1 over x minus 1. Notice that 1 is a bad point for this function. If you tried to plug in 1 to x squared minus 1 divided by x minus 1, you'd get 0 over 0, which is undefined. Yet, in this example, we're asking, what is the limit as x approaches 1 of x squared minus 1 over x minus 1? What is the limit of the function as x approaches this bad point, 1, that can't be plugged into the function? What we did last time with this is we noted that the numerator of our function is x squared minus 1, and that factors as a difference of 2 squares, and you get some cancellation. This function, x squared minus 1 divided by x minus 1, simplifies to x plus 1 through cancellation. You have to be kind of careful because this cancellation only works when x is not equal to 1. If x were 1, you'd have 1 minus 1 divided by 1 minus 1, and that would be undefined. It wouldn't be equal to 1, and it wouldn't cancel and give you the x plus 1. You cannot plug 1 into this function because you get 0 over 0. But otherwise, this function simplifies to x plus 1. So let's graph the function, and then we can talk about what its limit is as x approaches 1. If you graph the function x squared minus 1 over x minus 1, that just simplifies to x plus 1, as we indicated here. And x plus 1 is an easy function to graph. That's a straight line, slope 1, y-intercept 1. So it looks like this. But remember, you can't plug in 1 to our function, because if you did, you'd get 0 divided by 0. This cancellation only works here for x not equal to 1. So at x equals 1, there's a hole in the graph. And that hole occurs at a y-coordinate of, it happens to be 2, because that y-coordinate is 1 plus 1, x equals 1, and y is 1 plus 1, which is 2. And you can see here that if you take a little narrow strip around x equals 1, the number that x is approaching in this limit, your corresponding f of x values for these x values, they're going to be around 2. And as you make this open interval smaller and smaller, those corresponding f of x values get closer and closer to 2. So as x approaches 1, f of x is approaching 2. So the answer to our question is the limit as x approaches 1 of x squared minus 1 over x minus 1 is 2. As x gets closer and closer to 1, we can see that x squared minus 1 over x minus 1 is getting closer and closer to 2. And that's even more evident because this quotient simplified to x plus 1. So this limit is the limit as x approaches 1 of x plus 1. And it should be pretty clear there that what you're getting is 2. As x approaches 1, x plus 1 would have to approach 1 plus 1, which is 2. So here on this page, we have several ways of looking at the fact that the limit as x approaches 1 of x squared minus 1 over x minus 1 equals 2. More examples. Graphed is a function y equals f of x, and let's see if we can work out these limits. First of all, the limit as x approaches minus 5 of f of x. Well, here is minus 5, and let's look at this by taking a narrow strip through minus 5, and just looking at the graph around that narrow strip, which would be this little portion here. And I think you can see that as x gets closer and closer to 5, f of x is getting closer and closer to the y-coordinate of this hole in the graph, which looks like it's negative 1.5. So we would at least estimate that this limit as x approaches minus 5 of f of x is minus 1.5. For the limit as x approaches minus 4 of f of x, here is minus 4. Let's take a narrow strip around minus 4. And there, if you just look at that portion of the graph for those x values, you can see that as x gets closer and closer to minus 4, f of x is just going down to 0. So the limit as x approaches minus 4 of f of x equals 0. And then the limit as x approaches 2 of f of x. Well, here's 2. Look at a narrow strip around 2, and you can see that when x is close to 2, our f of x values, they are really close to 2 as well, y-coordinates of 2. And the closer and closer x gets to 2, the closer and closer f of x gets to 2. So the limit as x approaches 2 of f of x equals 2. For another example, think about the function f of x equals 1 over x squared, and it's graphed here. And look at the limit as x approaches 0 of 1 over x squared. Now in this case, as x gets closer and closer to 0, f of x is just getting bigger and bigger and bigger and bigger. In fact, if you take a narrow strip around 0 and look at the graph, I don't care how narrow that strip is, you're going to get parts of the graph inside this gray rectangle that just keep going up and up and up and up without bound. So here, f of x is not approaching any single number as x approaches 0. It's going to infinity. So because as x goes to 0, 1 over x squared doesn't approach a finite number, in this case, we have to say that this limit does not exist And that can happen for some limits. They will sometimes not exist. And we will abbreviate does not exist with the letters D and E. That stands for does not exist. So the limit as x approaches 0 of 1 over x squared does not exist. I'll show you another example of a limit that doesn't exist. This one involves the function y equals sine of 1 over x, which is graphed here, and it has an interesting graph. As x gets closer and closer to 0, the graph just oscillates back and forth between y equals -1 and 1, with the oscillations becoming tighter and tighter as x gets closer and closer to 0. And that makes sense because as x approaches 0, its reciprocal 1 over x is getting bigger and bigger and bigger. So sine of that is just oscillating up and down. So as x gets closer and closer to 0, sine of 1 over x bounces up and down between -1 and 1, oscillating faster and faster and faster the closer and closer and closer x gets to 0. So because sine of x, or sine of 1 over x, is not approaching any single number as x approaches 0, we would have to say that the limit as x approaches 0 of sine of 1 over x does not exist. In our next example, we'll modify this example very slightly by multiplying the sine of 1 over x times x to get a new function, y equals x times sine of 1 over x. And if you think about what happens there, in multiplying by x, when x is small, close to 0, it's going to scale down these y values that are between -1 and 1 to make them closer to 0. And the function looks like this. Here's the graph of y equals x sine 1 over x. And think about the limit as x approaches 0 of x sine 1 over x. The function's oscillating positive and negative as x gets closer and closer to 0, but it's getting closer and closer to 0. Here we have the limit as x approaches 0 of x sine 1 over x equals 0. So on this page, we've seen numerous examples of limits that exist and that don't exist. It's important that you read the text and work lots of exercises to make sure you have a good grip on this. Let's move on to a related topic, left and right hand limits. I have the graph of a function y equals f of x here, and you can see it has a break in it. And we're asking, what is the limit as x approaches 3 of f of x? That seems a little bit problematic because as x approaches 3 from the right, f of x is getting closer and closer to 4. But as x approaches 3 from the left, f of x is getting closer and closer to 2. A limit has to be a single number. It can't be equal to two numbers. What are we going to say this limit is? Limit as x goes to 3 of f of x equals 4, or 2, or the average of 4 and 2? Actually, in a situation like this, we have to say this limit does not exist, because f of x is not approaching a single number. We can salvage some information from this picture by creating what we call a right-hand limit. In this notation, there's a superscript of plus next to the 3. And we read this as the limit as x approaches 3 from the right. That superscript plus means that you are insisting that x approach 3 from the right. We read this as the limit as x approaches 3 from the right of f of x. And it's understood that this means, or stands for, the number that f of x is approaching as x is approaching 3 from the right. And you can see here that as x goes to 3 from the right, f of x approaches 4. So the limit as x approaches 3 from the right of f of x equals 4. Similarly, we're going to define what's called a left-hand limit. Superscripting the 3 with a negative means that we are restricting x to approach 3 from the left. And we read this as the limit as x approaches 3 from the left of f of x. And that value is 2, as you can see here. As x goes to 3 from the left, f of x approaches 2. So these are called right-hand limits and left-hand limits. The limit as x approaches c from the right of f of x is the number that f of x approaches as x approaches c from the right. And the limit as x approaches c from the left of f of x is the number that f of x approaches as x approaches c from the left. And it's a fact that in order for the limit as x approaches c of f of x to be equal to L, the right and left-hand limits as x approaches c of f of x, they also both have to be equal to the same number L. Otherwise, the limit as x approaches c of f of x doesn't exist. And that's illustrated in the picture here. So get some practice with right-hand limits and left-hand limits, work some exercises in the book, and we'll see this idea pop up from time to time as we go through this course. But for the rest of today, we're just going to be talking about regular limits. We'll talk about limit laws next. These are laws that allow you to simply evaluate or find certain limits. First of all, think about a power function y equals f of x, which is x to the power of n, where n is an integer. Your experience with these functions would lead you to firmly believe that if you take a number x equals c, whose y-coordinate on the graph is c to the power of n, then as x gets closer and closer to c, your f of x, or x to the power of n, would have to get closer and closer to c to the power of n. It's pretty obvious that the limit as x approaches c of x to the power of n equals c to the power of n. We're going to take this equation written here as a fact. It's going to be one of our so-called limit laws. Whenever you see the limit as x approaches a number c of x to the power of n, this limit law says the answer is going to be c to the power of n. Another limit law concerns the constant function y equals f of x that's equal to k, whatever value of x you plug in. And if you graph this function, no matter what x is, f of x is always equal to k, so it's just a horizontal line with y-intercept k. If you take any number c, f of c equals k. If you take any number x, f of x equals k. And as x approaches c, f of x, you might say it's approaching k. It's actually already equal to k. But you definitely have the limit as x approaches c of k equals k. The limit as x approaches c of f of x equals k, and f of x equals k. So the limit as x approaches c of a constant k equals k. And that's another limit law. So we're picking up a couple of limit laws now, and on the next several slides, we're going to look at other limit laws. And these will be very useful to us when we are computing limits. Let's tally them. Basic limit laws. We have the limit as x approaches c of x to the power of n equals c to the power of n from here. We also have the limit as x approaches c of k equals k, where k is a constant. By the same reasoning, you might convince yourself that the limit as x approaches c of a to the power of x equals a to the power of c. A to the power of x is an exponential function. It should be intuitively obvious that as x gets closer and closer to c, a to the x is getting closer and closer to a to the power of c. And we'll take that as a basic limit law. Also, the limit as x approaches c of log base a of x would be log base a of c. Your experience with log functions tells you that as x gets closer and closer to c, log base a of x is getting closer and closer to log base a of c. Now, this only works for c greater than 0, so c is in the domain of the log function and can be plugged in here. But we have a limit law. Limit as x approaches c, log base a of x equals log base a of c. So some examples here. Imagine you have the limit as x approaches 3 of x squared. That would be, according to this limit law, 3 squared, which is 9. So the limit as x approaches 3 of x squared is equal to 9. For another example, the limit as x approaches pi of x, well, that's a power function too, x to the power of 1. It would just be pi to the power of 1. By this law, the limit as x approaches pi of x equals pi. Makes total sense. You really don't even need a limit law from that. You can just do it in your head. As x gets closer and closer to pi, this function x is getting closer and closer to pi. It's approaching pi. So there's the answer to your limit. Here's another one. The limit as x approaches pi of 7. By this limit law, the limit as x approaches pi of 7 would be 7. And the limit as x approaches 1 of ln of x. Ln of x is log base e of x. According to this limit law, we should get log base e of 1, or ln of 1, and that's 0. So we have here 4 basic limit laws. And we're going to continue with our limit laws. For the next limit laws that will be on this slide, suppose that the limit as x approaches c of f of x and also the limit as x approaches c of g of x both exist. Then it should be clear that the limit as x approaches c of f of x plus g of x, the limit as x approaches c of the sum of these two functions would be the sum, limit as x approaches c of f of x, plus the limit as x approaches c of g of x. That as x gets closer and closer to c, f of x plus g of x is approaching the number that f of x is getting closer and closer to, plus the number that g of x is getting closer and closer to. That should be intuitively obvious and plausible. Later in the course, or not in this course, but maybe in more advanced calculus courses, you'll actually prove that this limit law is true. But for now, our point of view is that it's simply a very intuitively clear and plausible equation. And we're going to use this to evaluate or to find limits. Notice that it has the possibility of taking the limit of a complicated function, f of x plus g of x, and breaking that into the sum of two simpler limits. And that's going to be useful. Likewise, it makes sense that the limit as x approaches c of f of x minus g of x is the limit as x approaches c of f of x minus the limit as x approaches c of g of x. Likewise, if k is a constant, the limit as x approaches c of k times f of x should be k times the limit as x approaches c of f of x. This is saying you can factor a constant out of a limit. This is sometimes called the constant multiple rule for limits. Again, in a more advanced class, you can prove that these two things are equal, but I want to point out that this is very intuitively clear, or it should be. As x approaches c, k times f of x is approaching k times the number that f of x is approaching as x approaches c. It makes total sense if you think about it. Another limit law that breaks down a complicated limit into two simpler limits is this one. The limit as x approaches c of f of x times g of x is the limit as x approaches c of f of x, which is a number, times the number limit as x approaches c of g of x. So this limit law can potentially take a complex limit like this one and break it down into the product of two simpler limits. And therein lies its utility. Likewise, there's a rule for quotients. The limit as x approaches c of f of x over g of x is the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. And here, this is always going to work except when the limit as x approaches c of g of x is equal to 0, because then you can't divide by 0, and the rule breaks down. So this rule holds provided that the limit as x approaches c of g of x is not 0. Another limit law states that the limit as x approaches c of f of x to the power of n is the limit as x approaches c of f of x, whole thing raised to the power of n, which should make sense. And this is stated for an integer n greater than 0. So positive integers n. And finally, our last limit law states that the limit as x approaches c of the nth root of f of x is the nth root of the limit as x approaches c of f of x. This is just simply saying that as x approaches c, the nth root of f of x is approaching a number that's the same as the nth root of the number that f of x is approaching as x approaches c. And I'm sure that this looks believable. It's actually true. And again, later in a more advanced calculus class, you can prove that these two things are equal. But for now, take it on faith. You probably totally believe it anyway, because it is intuitively so clear. It's so commonsensical. Now watch out, this is defined for integers n greater than 0, just as we had up here. But also, the limit as x approaches c of f of x has to be greater than 0 if n is even. It has to be positive. And the reason for that is if n is even, you can't take the nth root of a negative number. So what's inside here, this limit, it has to be positive for this limit law to work. So you should remember these limit laws, but you'll get to the point where remembering them is really not an issue. They become second nature. You'll use them so often that you get to the point where you're not even thinking about it anymore. So it's important to work enough examples that you get to that point. Let's take a couple of examples. We'll do one here and then we'll move on to the next slide. Think about the limit as x approaches 3 of 4x plus 5. And I'll bet even without thinking about any of these limit laws, you have a pretty good idea of what that equals. But let's break it down using the limit laws. We have the limit as x approaches 3 of 4x plus 5, and that's the sum of two functions. So by this limit law up here, the very first one, this breaks up into the sum of two limits. The limit as x approaches 3 of 4x plus the limit as x approaches 3 of the constant function 5. And then by this constant multiple rule, a constant of k can come out of the limit. So this 4 can come out of this limit. And we get 4 times the limit as x approaches 3 of x plus the limit as x approaches 3 of 5. Now the limit as x approaches 3 of x, by one of our basic limit laws from the previous slide, is just x. And also, by one of those basic limit laws, the limit as x approaches 3 of the constant 5 is just equal to 5. So we get 4 times 3 plus 5 equals 17, which you probably already surmised, even before breaking this down with limit laws, it's pretty clear that as x gets closer and closer to 3, 4x plus 5 is getting closer and closer to 4 times 3 plus 5, which is 17. But the point is, if you needed to, you can apply these limit laws to break complicated limits down into simpler pieces and get an answer from that. Here's another example. The limit as x approaches 2 of 3x squared minus 4x plus 7. Let's see if we can break that down using the limit laws and get an answer to this limit. The first thing you could say is that this function is the sum of two functions. It's the sum of the function 3x squared minus 4x plus the function 7. So we could break this down as the limit as x approaches 2 of the first function plus the limit as x approaches 2 of the second function using our first limit law from the previous slide. Now we have, in part of this, the limit as x approaches 2 of 3x squared minus 4x. The second limit law from the previous slide would tell us that breaks up into the limit as x approaches 2 of 3x squared minus the limit as x approaches 2 of the other part of it, 4x. And then this limit as x approaches 2 of 7 just comes down. So we have a sum and difference of three simpler limits here. Continuing with this, we have a constant of 3 which can come out of the limit by the constant multiple rule, and the same with the constant of 4. So doing that gives us 3 times the limit as x approaches 2 of x squared minus 4 times the limit as x approaches 2 of x plus the limit as x approaches 2 of 7. Now we can use our basic limit laws from 2 slides ago. The limit as x approaches 2 of x squared would be 2 squared. The limit as x approaches 2 of x is 2. So we get 3 times 2 squared minus 4 times 2 plus 7, and that works out to 11. So we've taken a complicated limit, broken it down into simpler limits, and gotten the answer. You can imagine that in doing a problem like this, you're typically going to skip a lot of steps, and that's totally normal. When you first start out, use limit laws exclusively, you'll quickly reach the point where you are skipping steps, sometimes computing the limit in one single step, and that's fine and that's normal. I'd like to point out something that's happening here. We had the limit as x approaches 2 of this polynomial, and notice that in breaking it down with the limit laws, we eventually got to a point where we just plugged in 2, the number that x was approaching, into the polynomial and got the answer of 11. In fact, you can show that that always works. Theorem: if f of x is a polynomial, then the limit as x approaches c of f of x equals f of c. In other words, if you're ever evaluating the limit of a polynomial, as we were doing here, you can get the answer in one step by just plugging in the number that x is approaching into the polynomial. F of c will be the answer, with no limit laws. For another example, think about the limit as x approaches 2 of 3x squared minus 4x plus 7 divided by x to the 5th minus 3. Here we can use our quotient limit law. This is the limit as x approaches 2 of 3x squared minus 4x plus 7 divided by the limit as x approaches 2 of x to the 5th minus 3. And that's a polynomial divided by a polynomial, or rather the limit of a polynomial divided by a limit of a polynomial. So our previous theorem says on the top and the bottom, we can just plug in what x is approaching. So we get 3 times 2 squared minus 4 times 2 plus 7 divided by 2 to the 5th minus 3. Just plug in a 2 wherever you see an x. And that gives us 11 over 29. And you could see that this would hold, this trick that we used here would work whenever you have the limit as x approaches c of a polynomial divided by a polynomial. You could just plug in what x is approaching, plug in the c to get your answer. A polynomial divided by a polynomial is called a rational function. So to conclude this, if f of x over g of x is a rational function and g of c is not equal to 0, then the limit as x approaches c of f of x over g of x equals f of c divided by g of c. To get the answer, you just plug in the number that x is approaching, just as we did here. Now we have to stipulate that in order for this to work, g of c is non-zero, otherwise you're dividing by 0 right here. So be on the lookout for situations where you could use these two theorems that we've indicated. And as you know, as I've said before, you'll quickly get to the point where you don't even think of these theorems. You just apply these rules. It'll become second nature. Here's another example. The limit as x approaches 2 of the square root of the function that we had on the previous example, this rational function. We have a limit law that says the limit can go inside that radical. So we get the square root of the limit as x approaches 2 of this rational function. And inside the radical is exactly the problem that we worked in the previous example. And the answer to that was 11 over 29. So this limit works out to the square root of 11 over 29. So today, we've looked at the definition of a limit. We've looked at the geometric interpretation of limits. We've looked at right-hand limits and left-hand limits. And we've looked at limit laws that allow us to compute certain limits. You should get lots of practice using this, because coming up we're going to build on this. We'll have more limits. So work lots of exercises. This stuff will layer and build on itself. So be prepared for that. And I'll look forward to seeing you next time. Goodbye.